Hi everybody, this is Mr. Folly, and welcome back to the wonderful world of thermochemistry, where we're going to do stoichiometry with heat and bond energy. So let's hop right into it. Exothermic reactions put heat on the right, endothermic reactions put heat on the left. Either way, just treat heat as a product or a reactant in stoich with its coefficient as the number of kilojoules in a balanced reaction. So for example, if I have A plus 3B yields 4C plus 5 halves D plus 13.5 kilojoules. All you do is you treat heat just like any other reactant or product. The substance is kilojoules, and then 13.5 would be your coefficient. So if I had 3B, or let's make it harder, if I had 7.5B and I want to convert into heat, times dividing bar, 7.5B, 13.5 kilojoules, and there's your answer. Except for that's not 7.5 kilojoules, it's 3. And I'm really sorry I did that. The 3 comes from here. Okay. Sorry about that. This number was 3. This number's 3. So you could do that math, but really, who cares? Let's do some other problems. When potassium chloride decomposes, delta H for the reaction is 25.5 kilojoules. If it's 25.5 kilojoules, that would be a positive 25.5 kilojoules. So is my heat term going to be on the left or on the right when I do this? If it's positive, it will go on the left. Remember the Plendo thing? If delta H is positive, it will go on the left-hand side of the reaction, and it will be endothermic. So potassium chlorate is KClO3. And when KClO3 decomposes, it forms KCl plus O2. And to balance this, I'd have to put a 2 here, a 2 here, and a 3 here. Now, if the delta H is 25.5 kilojoules, I would have to sneak my 25.5 kilojoules here. Put a plus sign. Sorry about that. Let me just go ahead and rewrite that just for everybody's happiness. 25.5 kilojoules, because it's endothermic, it goes on the left, plus 2 KClO3 yields 2 KCl plus 3O2. Now, if it didn't say for the reaction, if it said for potassium chlorate, then I would have to divide everything by 2 and have 1s for coefficients. Okay, so the first calculation is if 25.5 grams of KClO3 reacts, how much heat is released? Times dividing bar, heat in grams, KClO3, 1 mole, KClO3. Little g stands for grams, and little g stands for go to the periodic table. Potassium is 39.1, chlorine is 35.45, and 3 oxygens would be 48. Add that together and I get 122.55. So now I'm in moles, so my grams of potassium chloride are gone. I'm in moles of potassium chloride, so I want to get rid of that. And I want to go into heat. Now I'm not going to call it heat, I'm going to call it kilojoules, because that's your unit for heat. And I need a relationship between kilojoules and heat. So my relationship is this, KClO3 and kilojoules. So my coefficients give me the relationship, 2 and 25.5. And that's it. These are actually a little bit shorter because you don't go through moles of heat before you do it. So 25.5 divided by my other answer times 25.5 divided by 2 is 2.65 kilojoules. Now, it doesn't really matter whether I put the kilojoules on the left or on the right, the number would be the same, but that's basically it. If 10.5 kilojoules of heat is released, how many liters of oxygen formed at 1.5 atmosphere and 35 degrees Celsius? Oh, you thought liters of oxygen. You could use the dreaded 22. I can't even say it. So I'm going to start with 10.5 kilojoules of heat times dividing bar. Hate you kilojoules, put them on the bottom. Always go through moles of oxygen. And then I need a relationship between oxygen, 3, and kilojoules, 25.5. Now, I am tempted to do the 22.4 liters, but don't you dare do it. It's never 22.4 because in AP Chemistry, they very rarely put you at STP. So I'm going to stop and get my moles right here. So 10.5 times 3 divided by 25.5 equals 1.24 moles of O2. Now I'm going to do PivNert. PV equals nRT. And of course, this is my N. The pressure is 1.5 atmospheres, and that's good for the R that we use. The volume is our variable. Our moles would be 1.24. R is 0.0821. Temperature is 35. 35 plus 273. I need Kelvin. 308. So my volume would be 1.24 times 0.0821 times 308 divided by 1.5, and I get 20.9 liters. That's it. Here's the table that is impossible if you're not stuck and frozen. So, oh, there it is. So, here's bond energies, and find delta H of formation for H2. Now, if I want to form H2, I would have H plus H, and that's going to make, I know I'm jumping ahead of the bond unit, but HH or H2. So in this case, all that's happening is I'm forming one H to H bond. So look at my little chart, which you see, I assume, and it says the H to H bond is 74. So my question is it positive 74 or negative 74? The bond is forming. Forming bonds releases energy. What's negative 74 kilojoule? Okay. Find the heat of formation for H2O. So here I would do H2 plus O2 yields H2O. So over here, everything on the left is going to break, and everything on the right is going to form. So I hope I'm not going to drive you too crazy with these things, and I do hope you remember one thing. If I were to redraw this, this would be H-H. I hope you would remember, actually I need to balance this, don't I? I hope you would remember that oxygen's double bonded. If not, I'm sure you'll believe me. So I have two H-H's, one O-double-O yields, we know water looks like Mickey Mouse, right? So I then get two Mickey Mouses and go this way. So everything that breaks is positive. So I have 2 times a hydrogen-hydrogen bond is 74, and it's positive, plus I only have one oxygen. The oxygen double bond is, oh, I did this wrong. I looked at the wrong column. The energy for a hydrogen-hydrogen bond isn't negative 74. It would be negative 436. I just looked in the wrong column. So if I have 2 hydrogen-hydrogen bonds, it's not negative 436. Well, it's 2 times negative 436. Plus, I have one O-double-O, and it's 498. And then that's going to be positive. Then plus, if I'm making 2 waters, I have 4 O to H bonds. So O to H from this wonderful little chart is 366. Now, if these are forming, they're going to be negative 366. Remember, forming is negative, breaking is positive. So 2 times negative 436 plus 498 plus quantity 4 times negative 366 and quantity. And I got negative 1838 kilojoules. Good. Come on. If water formation has delta H of negative 286 kilojoules per mole, what is the bond strength of O2? You know what? This thing's being so bad, I've got a better example. Phase change oddities. Changing state does not change temperature. So I forgot to do this before. So, phase change things that we were supposed to talk about. And I drew this badly. Let me put a new slide in here. Edit, insert blank slide. Widen up my pen a little bit here. Okay, this axis over here is kinetic energy. This axis over here is potential energy. So whenever the kinetic energy is increasing, your temperature is increasing. Whenever this is a phase change, and this would be, for example, melting. This is a phase change. This would be boiling. Some things to notice: when you're melting or boiling, your temperature is constant. In Excel, you may not remember this, but you sat and watched water boil for 10 minutes and saw the temperature didn't change. You really did. That was what we did to torture you. You sat and watched water boil. But something does change. What changes is your potential energy. So the potential energy means that bonds are breaking. So on both of those, bonds are breaking. And of course, you can also have a cooling curve, which would be where bonds would be forming. I do want to notice that I want to point out that this is longer and this is shorter. And that's because it takes more energy to go from a liquid to a gas, substantially more than it does to take to go from a solid to a liquid. All right, now we've got a couple of questions we can do and get out of here. Let's hope. If delta H negative 296, which the following statements are true, the reaction is exothermic. Plendo. Is it negative? Nope. The reaction is exothermic, so that is false. Right? When 0.5 moles of sulfur reacts, 148 kilojoules of energy. So 0.5 moles of sulfur times divided by moles of sulfur, and then kilojoules. So 296, and my coefficient is 1. So that means half of 296 is 148. That is true. All are true. None are true. Only 2 is true. Yay. Last one. Using the following bond energies. This is number 10 on your sheet. Estimate the heat of combustion for 1 mole of acetylene. So what we have to do here is know a little bit about what acetylene looks like, which isn't fair, but we're going to do it. So acetylene has 2 H's, which means it must have a triple bond. But look, it's the only carbon-carbon bond you're given. Okay, plus O2. There's no OO single bond, so it's an OO double bond. So I've got 5 halves of this. Yields 2 CO2. There's no C to O single bond, so it's a C to O double bond. Plus H2O, and there's 2 of these. H2O and H2O looks like Mickey Mouse, or H-O-H. Okay. So I have 2 C to H bonds, so 2 times C to H is 413, and these are breaking, so they're positive. Plus 1 C triple C, again it's breaking, so it's positive, 839. Plus, now I've got oxygen, 5 halves times O double O, which is 495. Again, I'm breaking it, it's positive. Plus 2, oh, not 2. There are 1, 2 bonds times 2, so I have 4 C double O bonds. So 4 times, and these are forming, negative 799. Plus, and then I have just 1 water, so I have 2 O to H bonds, which are 467, and since they're forming, they're negative. Now, we should know that since this is a combustion reaction, it'll be exothermic. So let's hope that it is. So 2 times 413 plus quantity 839 and quantity, I don't know why I did that, plus quantity 5 halves, what is that, 2.5, so 2.5 times 495 and quantity, plus quantity 4 times negative 799 and quantity, plus quantity 2 times negative 467 and quantity equals negative 1227.5, which is negative 1228, and that is B. And B stands for Boo, which stands for Happy Halloween, and we get out of here in under 15 minutes.